Okay. So the last video I talked about what ANOVA is, but then generally I don't want anything to go over half an hour for video lengths just because the videos get big and I do have to download and upload and do weird things with them. But anyway, so we talked about what ANOVA is, but we never actually did it. And you're like, that wasn't any fun. I know. So if I can properly pull the slides up with my little slippery fingers, we looked at this example from the Blumen text on cars and miles per gallon it's a really simple, easy to understand example. And this is just all on paper, no SPSS yet. And the Blumen table is this. This is what's called the ANOVA table. This is a carryover from the old days, my days, like people born like 50 plus years ago kind of people. This is actually like you needed this in the days before computers. You still kind of need it, and you will still see this in the SPSS output, even though reality is at this point in the game, all of these calculations could just be done behind the scenes and we could just get an F statistic, spewed out, which is kind of like how Excel would do this kind of stuff. Just here's a result, have fun. So, be aware that the whole sort of manual setup, it's good that it's good for understanding, good for the theory, but reality is it's the end game F statistic thing that we want. We also want the associated p-value that in the textbook examples, no p-values there, which is really annoying. But in SPSS, the p-value will be there. So what we're going to do is we're going to go into SPSS with this data and run this example and show you your very first way to run ANOVA. Now, yours truly kind of made a little mistake once when she set this up initially, but I actually really like these examples, so I don't want to change them. So this is the cars example, and then there's actually another one called MPG, which is also related to cars, but that's a separate example for the two-way ANOVA. So the one we're going to look at now is called cars, okay? Cars, very simple, cars, okay. So we have to look at a couple things. One, we have to look at how the data is set up in SPSS. And so the data set up in SPSS looks like this. I already typed it in. You're not going to watch me type. The 4 small cars, the 5 sedans, the 3 luxuries. 2 variables you need to have in this case. You need to have the group variable. Now this is just left as a string, just literally typing words in, and then MPG, of course, is numeric. Okay, so how do we actually run an ANOVA? And the answer is analyze, compare means, one-way ANOVA. This is the first way I'm going to show you. I actually don't like this way, but it's simpler and easier to show you like your first baby ANOVA example. Like many things in SPSS, there's different ways to do exactly the same thing because that's how you make life more confusing. You add like different options for doing the same thing. But the simplest thing is to go under compare means, one-way ANOVA, which is underneath our old friends, all the standard tests on means, and that makes sense. There's also another one here under general linear model univariate. I'm going to show you both. This first way, honestly, I probably shouldn't even show you because I don't really want you to do it this way, but it's more straightforward, more basic. So let's do it this way. Go under compare means, one-way ANOVA, and then you're like, well, where's the factor? Here we have a problem. This is actually why I don't like this way, because it's not sensing the factor variable because it's a string variable. Interestingly enough, if we do it the other way, which is the way that I like better, and go under univariate, then the factor variable's there and it's completely happy and fun and loves it and there's nothing wrong. And you're like, what's the difference? And the answer is, honestly, I don't really know. Back in the old days, the way this was coded would not work. We've seen this before in here. So if you want to run it the first way, what you have to do is you have to use your string variable unless you entered it the way before. We've seen this before. This is this back-end numerical coding and then labeling thing. We've seen this many, many times now. So what you have to do is you have to use that data. You have to go under transform, and you have to do something called automatic recode, and then click on it, and then give it a new name, size X, and then add new name, and then hit go. And then SPSS is going to magically create another variable which looks and smells exactly the same, except the new variable is a coded numeric variable with the values in it. Now, only the first way requires this. The second way, you can run it just fine without doing this. I don't know. I think the first way is probably like the old legacy way, and they never like reprogrammed it so you can actually do your strings directly. But the first way, you must do this automatic recoding under the transform menu and change the data from the string to a coded string where it actually does this for you, which I probably should have mentioned before because I think we've had to do this by hand once. So you have to do that. And then what you do is you go under data. I think recording. I don't know. I should probably make sure I'm recording before I start recording. If that makes any sense. So the first way is under analyze compare means, which is our old friend where all the t-test stuff is. One way, now it's there. So now the derived variable is there. You call it a factor because that's our new name for categorical variable. So not only are there multiple ways to do the same thing, there's multiple names for the same thing. No, no, I want a simpler world. The dependent variable is always your output variable, y. This, by the way, I just started using language of regression in terms of like input output. ANOVA is actually a kind of regression. And you're like, now I'm really confused. I know we're not going to really get into that in this class, but it is actually in the general linear model higher sense, and all the models are actually related. But this class kind of like ends at that because we're not really like a stats advanced class. So anyways, I have my variable and now I hit go and I get this and it's like, boom, I got my ANOVA table. Now, this right here is what I mean by a ANOVA table. We actually don't, for this class, we're not going to get into effect size. You could have just eliminated. This is what we want. There's our F ratio of 4.834. We go back to the Blumen slides that I lost in my giant pile of stuff that I have open. Right here, I scribbled all over it and I'm too lazy to erase my scribbling. But this F ratio of 4.83, bam, you see it in SPSS. That's how we get it. It's a lot easier to click buttons in SPSS than it is to do this all by hand. It's almost undoable by hand. I mean, I could probably do it if I like really seriously focus. The problem is not that it's hard to do, it's just that it's like all these little nitsy bitsy little picky little calculations that you're trying to make a little error here and there. So it's kind of like dangerous to do this by hand. But what's different about the table from the textbook and the table from SPSS is that SPSS has a p-value at the end where it says significance. You see 0.038. This is less than 0.05, not by much because it's a miniature data set. But we do in fact have a significant difference in the different types of cars. Yay! Okay. So I'm going to go back to the slides and tell you about one more issue because we need more issues. Okay. The issue, remember ANOVA's null and alt hypothesis. The null hypothesis is no difference. The alt is just that at least one mean is different from the others. That's all the alt is. But you're like, I want to know more than that. Okay. So what we want to do now is actually look a little bit more and drill down to figure out exactly where the differences are. This is actually super easy, thankfully. So, we have what's called a post hoc, which is Latin for I don't know. Okay. I went to Catholic school. I studied Latin. I forgot all of it. So I don't know what post hoc means anymore. But anyways, it will identify which means are different. It will conduct a second analysis after the ANOVA. You only do this if the ANOVA is significant. If the ANOVA is not significant, who cares? There's no difference between groups. There's nothing to analyze. But if there's some significance, which we have our p-value of 0.038, see, it's significant. So what we then want to know is where the differences are, because it's not necessarily true that there's a difference in all of them. We want to point out like where are the oddballs here and what exactly is the significance that we're looking at. And without doing that, all ANOVA does is tell you that there's a difference, which isn't like super interesting in and of itself. So anyways, after conducting this, there's several methods of doing post hoc. These I would not use. I should get this out of the slides because this is dumb. These are not formal hypothesis tests. Don't use them. I want you to do is something called a post hoc test, specifically the Bonferroni one. There's actually a whole bunch of these. And you're like, that's really hard and complicated. No. All you gotta do is click a button in SPSS and interpret it. So what this will look like in SPSS is you'll see something like this, which is at first kind of hard to look at. So this thing called multiple comparisons. We only have three groups, 1, 2, 3. So what this is doing is it's doing size cat 1. Now I don't know, this is the variable coding. I think this is probably sedans or small cars versus sedans, small cars versus luxuries. So if you think about it, if you have small and then like sedans and then luxuries, you have 6 comparisons: small to lux, small to sedan, lux to sedan, Yeah, you have six comparisons. Well, technically you have six comparisons, but reality is you only have um they're redundant. So like small to lux and lux to small, this is really the same thing. And you see that here. So really you only have one, you have these three, and then they're duplicated in their opposite order. But where are the differences in what the heck is this showing? And the answer is here. The significance column here, which ones are less than 0.05? So the one that's less than 0.05 is 3 to 1 or 1 to 3. See that? These are actually redundant. 1 to 3 is here, and 3 to 1 is here. Now, these are both very slightly less than 0.05. These p-values aren't directly the same as the other p-values. So these are the comparison. Now, we do have a p-value less than 0.05. That's the 3 to 1. So here's your significant difference. The others are not. 1 to 2 is not significant, and 2 to 3 is not significant, but this one is. So that's what the postdoc thing is telling you. But I also have to show you how to run this in SPSS because your life would not be complete without such a thing. I may end up with 5 or 6 videos on this one. Oops. Yeah, I have a feeling that's going to happen because I don't want to go into like 65-minute videos. But well, let's go back in SPSS. So we ran the basic ANOVA, but you're like, how do I get that postdoc thing? Okay. Yeah, so the postdoc thing, post hoc, whatever that means. Back to the data. I had to make this, in order to do it with this method, I had to make this crazy little this derived variable because this variable is a string. This method will not process that. The other method actually will, which I don't know why. I guess, I mean, for legacy purposes, they keep all the old stuff in with the new stuff. It's kind of like a library where you have like 90-year-old, you know what I mean? Anyways, so under here, let's go to compare means and let's go to one-way ANOVA. Same place we were before. How do I run post hoc? Well, just how about that post hoc button? Yeah, that's cool. Now, here's another thing. I actually did once understand this. I went to grad school specifically in stats, not like math stats, like stats. Like all of my courses were stats. And literally, I had entire courses that covered like all of the exact differences between all of these different kinds of tests. And the answer is right now, I no longer have even the slightest idea. They're actually different methods. They all do this. I think this kind of like wins an award for like the biggest number of methods to do. And I don't know what the subtle and weird differences are anymore. I generally just go with the one called Bonferroni because that's the one that I've used the most. That's actually the one I use like with microarray data and biological stuff. So it's just like it works. Use it. Don't. So when you go under here, just check Bonferroni and use that method. You could actually research what all of these other methods mean. I don't know anymore. I used to know. There's a lot of little tweaks and like, flavor varieties, but it's the same thing essentially. So check off that Bonferroni, hit go, and then you get this. Now we don't need this effect size table. I could get rid of that. So now we have our multiple comparisons table, and you see now mine actually has the actual labels on it. The other one might not have checked. Like, so I have, instead of 1 to 3, I have although the other one was mine too, but it was from a long time ago that I ran this. So now when I rerun it with my newfangled variable, I do get luxury to sedan, luxury to small. And you see where our significant differences are, which it's the luxury to small that the biggest difference is. Okay. And this is the only one that would be significantly different. So this is where the significance, the reason this is less than 0.05 and the two groups that actually differ are the luxury and small cars. Okay. That's the Bonferroni correction. Yes, this is going to go to 6 videos. I can't keep going on one video. It will be like, we're going to be looking at 2-hour-long videos. No. Okay. So I'm going to stop this and then I'm going to pick up and we're going to do this humongous example on broccoli, which you're going to be just delighted to see. Okay.